Hello there, welcome to the sixth and last knowledge clip for chapter 5, which is part 5 of chapter 5. Today we are going to talk about the temperature dependence of the equilibrium constant K, and we are also going to talk about the so-called osmotic pressure. Okay, so what you see here are glass containers, and they contain secondary glass compartments in which there is a gas that has a brown color. And that gas is nitrogen dioxide. Nitrogen dioxide can be formed out of dinitrogen tetroxide. Dinitrogen tetroxide is a colorless gas, while nitrogen dioxide is a brown gas. So you see from left to right with the color, there is a larger amount of nitrogen dioxide in each vial. The one on the left is at minus 10 degrees Celsius, the one in the middle at 0 degrees Celsius, and the one on the right at 80 degrees Celsius. So if we plot for each one of those the Gibbs free energy against the amount of or the mole fraction of the nitrogen dioxide on the x-axis ranging from 0 to 1, then we find at minus 10 degrees Celsius that the lowest value for the Gibbs free energy is actually at a small fraction of nitrogen dioxide. That means at minus 10 degrees Celsius, the equilibrium is shifted to the reactants. At 0 degrees Celsius, actually, the equilibrium is right in the middle, where you have a 50-50 mixture of dinitrogen tetroxide and nitrogen dioxide. At the high temperature, the equilibrium is shifted to the products, to the nitrogen dioxide. And you have a majority of nitrogen dioxides in the gas. That's why the gas becomes so brown. So you see, the equilibrium seems to depend on the temperature here. And you can also see that the standard Gibbs free energy change of reaction is larger than 0 at minus 10 degrees Celsius, which means it's not spontaneous towards the formation of products. At 0 degrees Celsius, it's 0, and at plus 80 degrees Celsius, the Gibbs free energy of reaction is, at standard conditions, smaller than 0. So you see, the Gibbs free energy of reaction depends on the temperature, and that originates from the temperature dependence of the equilibrium constant K. What is that temperature dependence? That is given by the so-called Van 't Hoff equation. The Van 't Hoff equation is nothing else than the combination of this equation with the already established equation for the Gibbs free energy, which is the enthalpy change minus the temperature times the entropy change. So the fundamental equation, which is basically the combination of the first and the second law of thermodynamics. So combining these two gives us the Van 't Hoff equation. So just the right side of the equilibrium constant equation and the right side of the Gibbs free energy definition equated gives us, when we rearrange it, the so-called Van 't Hoff equation, where the natural logarithm of the equilibrium constant depends on the temperature, which you see here in the denominator. It also depends on the magnitude of the enthalpy change at standard conditions and the entropy change at standard conditions. So this is the important Van 't Hoff equation that is used to describe the temperature dependence of the equilibrium constant. Let's look at an example. The dissociation of water. When you have pure water, with no other additives, it will spontaneously split into, at least a fraction of the water will spontaneously split into protons and hydroxide ions. So there's an equilibrium constant for that. The equilibrium lies mainly on the water, on the undissociated water, but a small fraction forms the protons and the hydroxide ions. So that equilibrium constant is much smaller than 1, but it can be calculated simply with the concentration of the protons and the concentration of the hydroxide ions. And in the definition of the equilibrium constant, you also would have to take into account the reactants, which is the water, but since the water concentration is constant, as we've seen before, it can be considered 1 in the definition of the equilibrium constant. So that is basically the equilibrium constant for the water dissociation, which is our example here. And I can just write it in form of the Van 't Hoff equation, as you've seen here. So I just take out the temperature here as 1 over T, and you'll see in a moment why I do that. So the concentration of the protons and the concentration of the hydroxides, they can be measured in an experiment at different temperatures. And then you can calculate the equilibrium constant and plot here on this scale the natural logarithm of that equilibrium constant. If I plot that now against 1 over the absolute temperature, which you see in the Van 't Hoff equation is the variable that is changing here, 1 over T, right? What I get is a linear line. These points here, they are the measured values for the equilibrium constant at certain temperatures. And then I just took the natural logarithm of that and fit that line with a straight line. And you see, the Van 't Hoff equation basically is a equation that describes a linear line, because you have a constant prefactor times that variable 1 over T plus the y-axis intercept, which is composed here of the entropy. So fitting this straight line here allows you to extract the slope of the line, which simply is the prefactor here, which is the negative enthalpy of reaction divided by the gas constant. So from that fit, basically, one can extract the enthalpy of reaction at standard conditions, which is in that example positive 55.9 kilojoules per mole. What does that tell us? The water dissociation has a positive enthalpy of reaction. When the enthalpy of reaction is positive, that means it's an endothermic reaction. It means energy has to be added to the system to trigger, in this example, the dissociation of water. So the dissociation costs energy. This positive value of the enthalpy of water dissociation has important consequences for the so-called neutral pH value. So, you know, water splits. So if you have pure water, a small fraction of the water molecules will split into protons and hydroxide ions. The amounts of hydroxide ions and protons, they will be the same, right? Because each water gives 1 proton and 1 hydroxide ion. Okay, so the pH value is a measure for the concentration of the protons, right? It's the negative logarithm of the proton concentration. Now, as you saw here, the dissociation constant of water depends on the temperature. And it's actually that due to the positive enthalpy of the dissociation, that with increasing temperature, you will have more dissociation. Because dissociation costs energy. You have to add energy to make the water dissociate. And by increasing the temperature, you increase the degree of dissociation. And that results in a temperature dependence of the neutral pH value, where the concentration of protons and the concentration of hydroxide ions are the same, which you see in this table. We all know the neutral pH value is 7, right? But this is only true for 25 degrees Celsius. At 0 degrees Celsius, the neutral pH is, for instance, 7.47. At high temperatures, such as 60 degrees Celsius, the neutral pH is pH 6.51. That is because at the high temperature, the dissociation happens more, and therefore more protons will be in solution, and therefore you have a lower pH value, right? So that's the reason why the neutral pH, which is the pH at which the concentration of OH minus equals the concentration of H plus, depends on the temperature, because of the temperature dependence of the equilibrium constant. And in this specific example, it's because the dissociation of water is an endothermic reaction. So more generally, actually, if you increase the temperature, it causes the equilibrium constant for an endothermic reaction to increase. If you increase the temperature for an exothermic reaction, the equilibrium constant actually decreases, right? Okay. In the second part of this knowledge clip, I want to introduce you to the concept of the osmotic pressure pi and the related chemical equilibrium. What I draw here is a container that has two openings. The container will be filled with a liquid, which is component 1, a solvent. Then I will put a dividing barrier in the middle of the container, and that is actually a semi-permeable or an osmotic membrane. That will separate the container into a right and into a left side. Into the left side, I will add solute molecules, which could be sodium chlorides, sugar molecules, or proteins, any of those. Those are components 2. The semi-permeable membrane is designed so that actually only the solvent can pass through it, either from the left to the right or from the right to the left. The solute cannot pass. The molecules may just be too big to fit through the holes of this membrane. As a result, an osmotic pressure will build up in the left compartment, which will cause the liquid level to rise in this column here. We can measure the height of the liquid rising to actually determine the osmotic pressure. So for our analysis, let's take a look at the chemical potentials of the left and the right reservoirs. First, the left reservoir. The left reservoir, the chemical potential of the solvent, component 1, is simply the chemical potential of the pure solvent, indicated by the star, plus the concentration dependent term, or here mole fraction dependent term, right? In the right compartment, on the other hand, the chemical potential of the solvent is simply the chemical potential of the pure solvent, since there is no solute in it. Okay, we know that at equilibrium, the chemical potential in the left and on the right for the solvents must be the same, right? That's what we already established in previous knowledge clips. But initially, in the left compartment, the chemical potential of the solvent will actually be smaller than the chemical potential in the right compartment. Why is that? Well, initially, the concentration of the solute, or the mole fraction of the solute, the mole fraction of the solvent, I mean, in the left compartment is smaller than the mole fraction of the solvent in the right compartment, because there is also the solute, which will basically reduce the mole fraction of the solvent. And if that mole fraction of the solvent is a number that is smaller than 1, then this logarithm will become negative, and that will make the chemical potential become smaller than that of the pure solvent, right? So what happens as a result is, due to this difference in the chemical potential, where we have a lower chemical potential on the left and a higher chemical potential on the right, there will be a transport of solvent from right to left. And that will cause the pressure in the left container to increase, because we add more molecules to the left, more solvent molecules. And as a result, and that will happen until the chemical potentials in the left and in the right are the same, which is the equilibrium conditions. So the resulting increase in the pressure on the left is simply the pressure on the left minus the pressure on the right, and that is the osmotic pressure. And the important formula that can be derived is this one, which was first discovered in the early 20th century by Van 't Hoff as well. So in exercise 5.5.4, you will be able to derive this formula yourself. It's quite a challenge, but you can do it. You will need the Maxwell relations, which you also can find in the study guide. So you see that the formula for the osmotic pressure shows that it actually only depends on the concentration of the solute, C2, and it does not depend on the type of the solute. Could be sodium chloride, could be sugars, could be proteins, any of those. They will, depending on the concentration alone will increase the osmotic pressure. You can measure the osmotic pressure, delta P, via the height of the liquid column that will rise as a result of the pressure, basically. And you can actually observe in biology an important implication of the osmotic pressure, which is that, for instance, red blood cells, if you put them into water that is not containing a lot of solutes, they will start to build an osmotic pressure, and they can even eventually burst, just because of exactly this effect that the water from the outside will want to go into the red blood cells due to the higher solute concentration, and they can then as a result burst, which is a dangerous thing. So don't drink distilled water. You can also use the concept of the molar mass of the osmotic pressure to measure molar masses of macromolecules such as proteins, which is an important experimental technique in experimental biophysics and chemistry. And then last, take a look at the shape of this formula for the osmotic pressure. It looks very similar to the ideal gas law, which is written here, because you can just express the concentration as the number of moles per volume, which you see looks very similar. So actually, a dilute solution, if it is ideal, can behave quite similar to an ideal gas. The solvent can be called a so-called dressed vacuum, which you can read more about in the study guide. That brings me to the summary of Chapter 5. In Chapter 5, we spoke about equilibrium during the exchange and conversion of matter. We learned that the chemical potential are the same at equilibrium for different regions of a cell, for instance. The equilibrium constant K is given by this important formula that connects it to the standard Gibbs free energy change. The standard Gibbs free energy change can be calculated with the Gibbs free energies of formation. Next time, we are going to talk about the thermodynamics of processes that involve electron exchange. Thanks so much for listening. See you soon.